Guys, 9.3 is titled Similar Right Triangles. All right. Guys, when I talk about similar right triangles right here, I'm going to kind of jump ahead and jump around a little bit. Whoops. Whoa. Okay. Similar figures. I've got a little typo here. I'm going to change this. Just get rid of this. Get rid of that right down there at the bottom. Okay? And we'll come back to that. That's a mess up on my part. But we're going to talk about similar figures, and then specifically we're still dealing with what kind of triangles, kids? Right triangles. So we're going to talk about the following. We're going to talk about how are altitudes, and this is going to be new for you today, geometric means of a right triangle related. Okay? A geometric mean is kind of like this. Well, I'll show you here in the definition in a second. But a geometric mean, I'm going to put this down right here. What's it say right there, kids? Uses proportions. What's a proportion, kids? Two fractions that are equal. So as an example, you might have like maybe 1/3 would equal 3 over what, kids? 3 over 9. Both would reduce to 1/3, wouldn't they? So when we talk about geometric means today, we're going to use idea of proportions to solve that. So if you kind of remember proportions, kids, really proportions, you guys remember the phrase cross multiply and divide? Have you heard that before? Okay, cross multiply, divide, that's going to kind of show up today. So the question we're trying to answer today is how are altitudes and geometric means of right triangles related? We're going to explore that today. I think this will make pretty good sense to you. All right. So goals in terms of answering the question, we need to identify similar triangles. We're going to look at some real life problems relating them. And this will be kind of new for you today, using geometric means. Although it's a new term, you've kind of done it before by using proportions. So let's get started on vocab first. Guys, a geometric mean is the following. It's the geometric mean of what type of numbers here, kids? In this case, A and B is the positive number x that satisfies the following. A is to x as x is to b. The example I gave you was 1 over 3 was equal to what?
3 equals 9.
Okay, you have two fractions that are equal to each other, and what they're saying is this. You would say the following. What you're looking at kind of is this. Is there a number in both of those fractions where there's the same numbers? One is in the numerator of one fraction and the other one is in the denominator of the other fraction. What is that value? It's 3, isn't it? So what we would do here, guys, is this. That 3 becomes kind of an interesting number because if I look at this and this, what I say right here is like, oh, I see a 3 down here, I see a 3 up here. What that means, kids, is this. It means 3 is I'm going to abbreviate GM of, let's go 1 and 9, right? Okay. All right, so what the heck does geometric mean here? Okay. Here's the deal. What do we say the geometric of 1 and 9 is? 3. It means that there's a number in between 1 and 9 where if you start here, multiply by something to get here, and then multiply by something again to get here, you are at what? 9. Well, what would you multiply by? What would be in here? Multiply by 3, multiply by 3. Now let me try to trick you. Let's see how good you guys are. I'm going to do this. I'm going to ask you the question. What's the geometric mean of... How do I want to do this? How about 2 over something equals something over 32? Okay. Think of it this way. Anybody know what those two blank numbers might be that are the same exact number? Okay. What's 2/8 reduced to, kids? What's 8/32 reduced to? Okay. Here's the best way to think about this. Kids, what's 1 times 9 make?
9.
What's the square root of 9? 3. Okay. That's why the geometric mean is 3. What's 2 times 32 make?
64.
What's the square root of 64? 8. Okay. So let me do one more here.
4.
How about 5 is to something as, why did I do that? Okay, as something is to 20.
10.
How'd you get 10 so quickly, Logan?
5 times 20 divided by our square root.
Yeah, so what is that 5 times 20 for a cross product, kids? 100, right? What's the square root of 100? 10. Okay. Guys, what would 5 over 10 reduce to? What would 10 over 20 reduce to? So what's the geometric mean of 5 and 20? Okay. Let me get a show of hands here. Geometric mean concept. Does that kind of make better sense then? It is a proportion, but in the two fractions, the denominator has to match a numerator in the other fraction. Okay? I'm going to put two fractions up here on the board. Top one or bottom one, which is an example of a geometric mean a model. Why the bottom?
This has 15 parts.
The 15s, right? Okay. They have to be in different ratios. One has to be in the numerator, the other has to be in the denominator. What's the problem with this one right here?
It's not.
Yeah, I don't see anything common, first of all. So that's a problem. Okay. Are we cool with geometric mean definition? Okay. Next thing we need to talk, altitude or triangle. What's another good word for altitude, kids?
Height.
Kind of like the height, you bet. Right? It's like the height. And we're going to talk a lot about altitude. So anytime you hear me say altitude, assume what? Height. So here's a triangle. I'll do my best to draw a little triangle. I am a little triangle.
You
Okay.
don't even know.
How's that triangle for you? Okay. I don't know why my sides are dotted today.
I like the dot.
Do you? You want me to keep the dots?
Yeah.
Okay. I can do that. And altitude then, simply a what, kids? Height. Okay, let's do it this way. Ooh, orange and black, my old high school colors. Whoa.
What was that?
Charles City Comets.
That's where I'm
Who did?
That one.
Amelia?
Yeah, I'm just.
Who's Amelia? Now guys, if I have an altitude in here, the assumption is when I go from a vertex of the triangle down, I don't like that top part up there. Let me get rid of that. D is D-U-N, done. Boom, goodbye. If I have an altitude in here, what's the assumption about this line going down to the base? Or to any other opposite side? What angle must be formed down here if it's a height or an altitude? Yeah, you don't, if I say I'm gonna measure your height, I'm not gonna stand somebody up at a 45-degree angle and measure their height. You know what I'm saying?
Yeah.
Isn't there a tower that doesn't stand straight up? somewhere?
Leaning Tower of Pisa.
Yeah, the Leaning Tower of Pizza. I've eaten pizza in that place before. It's good. All right. Where is that tower? Leaning Tower of Pisa, right?
I think it's a.
Is it Greece?
Yeah.
Is it? I have no idea. Right? Greece is a country I wouldn't mind visiting sometime. I think-
Isn't Greece the one with the white buildings?
The columns?
Boy, you're asking me hard questions.
No, all the buildings are white.
Is it there or is that Rome? I don't know.
Greece, all the buildings
Could
are
be.
white, right?
I don't know. I honestly don't, Michaela.
You know that you're able to go to sport events?
Michaela, is this bad to say? I'm just a stupid math teacher.
I don't know anything.
I don't either. I feel bad. I know my house is brown.
Our house is white.
Is it?
Yeah.
You live in the White House?
Yeah,
Cool.
in DC.
Sweet.
Yeah, I fly.
I'm so excited. My middle daughter and I get to go on a 4-day tour in 2022 to go do all the stuff in Washington. I'm excited to see all that stuff. So,
Why
For
just
what?
you and your
because
middle
my
one?
wife and my first daughter are going to go this summer.
So you take
Following
turns.
summer, I'm going to go with Lucy, and then I don't know who's going to go with Annie when it's her turn. So.
Both.
Okay, guys, what I want you to write down similar figures, write this down. Same shape. I screwed this up big time. Should be same shape, but different. What's the word I should use? Same shape, but different.
Soft.
Yeah, guys, two figures are considered similar, so I don't know. Gosh, I used to have my race cars up here. Actually, I do have a race car.
Supposed to be exactly the same.
Here's a race car.
You have a Buzz Lightyear.
I have Buzz Lightyear. Here's my Capital One Chevrolet. All right.
Who drives that?
Well, right now, Ron Chestnut drive it this year, but Kyle Larson drove this whatever year this was. But anyway, it's a Chevrolet. That's really all that's important there.
You like
Race
Kyle?
car lot?
I do not like Kyle.
No one does.
What about Logano?
Nobody likes it.
I kind of like Logano a little bit.
What?
Yeah. But listen, I'm a Chevy
Isn't he
guy.
the one that wins every race?
No, that would be Kevin Harvick.
Oh.
Yeah, Kevin Harvick's the
Kevin Harvick's a good driver, but he drives a Ford. So
No, I think it's
That's
It's
why-
not his fault,
why do you think
though.
he wins?
I understand.
He wants to
I drive
drive a
a
Chevy,
Ford
but it's
too,
not his
but-
fault.
I was glad to see Chase Elliott win the title last year. That was fun. Is this the real thing?
That's my brother's favorite.
No.
It's racing.
I like Chase Elliott too.
What's the one, Matt
No,
DeVito?
Chase
Matt
Mitchell.
Donatello's got a funny name, doesn't he?
Yeah, that's my favorite.
Same size as a real car?
Yeah.
This is what they're really racing out there?
Yeah.
Man, Kyle Busch is a little dude.
You know how long that would take to do the
He's like,
Daytona 500?
That's in 37 days, by the way.
they eat the little cookie from Alice in Wonderland.
They did? But this could happen, okay? All right, but this is gonna be something that would be a model. This is similar to a real race car because it's the same shape, but what? Okay. Oh, these are so cool. I just want to play with the cars now today. That's all I want to do. All right.
What do you do with that?
Look at that.
Well, this is a Talladega car. I came with my program when I went to Talladega. This was 2005. I was at Talladega in 2005. And in 2006, I've told this story to a lot of classes. You guys know the movie Talladega Nights, right? They were actually filming part of the movie a year we were there. It was pretty cool. You know the part where they run and dive across the finish line?
Yeah.
Yeah.
We had seats pretty much on the finish line that year in 2006, and they did like the stuntmen that were out there. They were taking a bunch of shots of them doing that. So I bet they probably dove 20 times onto that just to get the right shot for that movie. But it was neat.
That means that you're in it.
Well, maybe it's possible. I've never really looked really closely, but it was pretty cool.
You're
I was
an extra. They should have given me
I
money.
know. Should have gotten money for that.
So you saw Bill.
What's that?
You actually see Will there.
He was actually the grand marshal for the race that day. So he's the one that said, gentlemen, start your engine. That's cool. So, yeah. Okay, hey, I need you to draw a triangle again. I'm going to do my best to draw this. I need you to draw one that looks like, oh, how do I want to do this, kids? How about here? Here. Okay. Do it so your right angle is kind of up here. So this is kind of a 90-degree angle like this, okay?
What's that line? What's that supposed to be? In the corner. Can you see it?
Here?
It's the pen.
Oh, it's just,
Oh, it's my little pen. I'm sorry. Oh, this thing.
yeah, it looks like a line.
Sorry. Okay. Draw that in here, and then draw an altitude in here. Drop this altitude right in here if you can. Okay. Guys, if the altitude is drawn to the what? Okay, so let me put some angles in here like so. If I put this as a right angle like this up here, doesn't that make this the hypotenuse down here?
Yeah.
Okay. And so, what really ends up happening here, kids, is this. I gotta think about this for a second. Label this A, B, C, D like this. A, B, C, D. I'm not gonna get too wrapped up in what this core concept is, but what it says is this. If the altitude is drawn to the what? Okay, isn't A to B the hypotenuse in the big triangle on the outside here? There's an altitude that comes from across the hypotenuse down to the hypotenuse. It says this. It says then the two triangles formed are similar to the original triangle. Okay? I'm going to call this basically triangle 1 over here on the left, triangle 2 here. Do you guys agree that triangle 1 and 2 make up a big triangle all the way on the outside?
Yeah.
So how many triangles are really formed here when I drop that altitude in? Okay? What I really want to say here is this. When this happens right here, you don't really need to worry about all this stuff down here. What really ends up happening is this. In any right triangle, when I drop this in here, this will form a right angle down here. What really ends up happening is we form 3 similar triangles. Okay? So I'm going to put some stuff in here. I'm going to simplify what's written right here. What this means is this. Triangle 1, they use a symbol right here for similar. A little squiggly mark like this is going to be similar to triangle 2. Okay? Triangle 1 might have a name A, D, C, or something like that, or A, C to D. They name that right here. Okay? Also, I'm going to write this. Triangle 1 is also similar to, is it okay if I write the word big for 1 and 2 put together, or the one all the way on the outside? Okay? So, I could. The third triangle, I'm just going to call it the big triangle. Is that okay?
It doesn't.
Okay. And also, it says triangle 2 would also be similar to the big triangle. Okay? So how many similar triangles are formed, first of all? 3 of them. Okay? Now, here's what I'm going to tell you real quickly. When we start looking at this right here in terms of what's similar, what ratio should be, here's what I'm going to do. Use abbreviations like this. Okay. What do you think SL is going to stand for in terms of a right triangle?
Short leg.
What do you think LL is going to stand for?
Long
What do you think H is going to stand for? Okay. We're going to talk about each triangle in terms of what's its short leg, what's its long leg, what's its hypotenuse. And if I set up a ratio like this, if I set up a ratio that says, okay, in one triangle I'm comparing the short leg to the hypotenuse in one triangle, I better set up the other ratio as what to what if we're going to have a proportion or things work. Well, if one ratio is compare short leg to a hypotenuse in the first ratio, I better darn well compare what to what in the second ratio. Not long leg. We want to keep everything the same. We want to keep short leg to hypotenuse. So let me show you what's going on here today, kids. If I drop an altitude in a right triangle to the hypotenuse, how many similar triangles are formed? 3. Okay, let's talk about why that is. It says identifying similar triangles. Okay. Kids, you have a diagram right here. Okay? I think that when you name triangles, you should name them in this order. Okay? Go short leg, long leg, hypotenuse order. Okay? So let's start with this first triangle right here. Okay? I like to put a 1 here and a 2 here. And you guys understand the big triangle is from Q to M to P, right? Q to M to P is the big triangle. So, here's what we're going to do. Identify similar triangles, one set. Let's compare 1 to 2. Is that okay? All right. So let's do this. Guys, triangle 1. What's the short leg? What length?
Punch.
M to what?
N.
And then what's the long leg?
N to Q.
And then the hypotenuse would come back from Q to what?
N.
So I'm going to name the small triangle, or triangle 1. I'm going to say triangle M, N, Q. Okay, so I'm going from M to N, short leg, to Q, long leg, and then the third part is hypotenuse. Let's compare that to triangle 2. What's the short leg in triangle 2 there in that drawing?
Q to N.
Q to N. So I say it's similar to triangle Q to N. And what's the third vertice of that triangle 2?
N to P.
Q to N to what?
P.
P, okay? What that tells me, guys, is this. When I label stuff like that in this order, in triangle 1, the distance from M to N would match the distance from what?
Q.
I would say that they would be proportional. We would be comparing M to N is a short leg in triangle 1, isn't it? We would be comparing that to a short leg in QN right here. Isn't that the short leg of triangle 2? Would you guys agree with that? Yay or nay?
Yeah.
Okay, let's compare triangle 1 to the big triangle. Okay, so let's go in the same order. I think it's good to start your order by going short leg to long leg to what? Hypotenuse. Okay, so start me out in triangle 1 again. What's the short leg length and then the long leg length after that? What order should I go in?
M, N.
M, N, Q, right? So I'm going to say triangle M, N, Q would be similar to triangle. Okay, we're in the big one now. Okay, what's the short leg there again, Hunter? M to Q. I just don't know what order yet, but then I want to go to the long leg after that. So the long leg in the big triangle is Q to P. So I'm going to say triangle M to Q to P. Guys, when I say, when you name triangles to compare them as similar triangles, do you understand what I'm saying by probably go this order to keep things organized? Go short leg, long leg, hypotenuse when we're comparing them. Cool with that? All right, I'm not going to say a word. We have to compare triangle 2 to the big one as well. When we name what's similar. Again, similar means same shape, but what?
Different size.
Different size. All right, who wants to take a shot at this comparing 2 to the big one? Going short leg, long leg, hypotenuse. What do you think, Logan?
Q to N to P.
Q and P, so short leg, long leg, yep, hypotenuse. So let me write that down. Triangle Q and P would have to be similar to triangle.
N, Q, P.
All right, so M is short to Q, short leg in the big one, to P, long leg, and then P back to M would be your what? Hypotenuse. So that order goes what again there, Logan?
M, Q, P.
M, Q, P. It's my finishing move in wrestling, the M, Q, P.
How come we don't, how come we don't add the M back to the end of it? Like to say that it could be.
It's weird, isn't it? They don't do that because they think, man, what can end up happening is if you label M here twice, you might say, okay, some people might start working backwards and going M to P to Q if they do that, by putting another M back there. So it's kind of like an order of doing things. So, and they always name stuff based on how many vertices you have. So a triangle's only going to have how many corners? 3. So if I have a 4-sided figure, you would only name it by. That makes sense. And part of that's because they're like, if I see 4 letters, they might think 4-sided figure. That makes sense to you too?
Yeah.
So that's why they choose not to do that. That's a great question, though, Hunter. Okay, let's talk about this. Modeling with mathematics. Here's a good question. It says a roof has a what? So I'm looking at the roof from the side of the house. Here's my roof. Okay, this looks like a pretty neat home with a roof like that. Okay, I've always wanted to build an A-frame house. Anybody live in an A-frame?
What's that?
So it's like they're shaped like this, and they go all the way down to the ground just like that. There's no like sides to it. They have like a big loft in it, and then the bottom is like wide open. And look up A-frame house on Google someday. Okay, they're so cool. I'm gonna build one and live in one before I pass here. The diagram shows the approximate dimensions of this cross section. Find the what?
Height.
We gotta find this height of the roof right here, kids. Okay. First things first. Do I have a big right triangle?
Like a
Yes.
triangle.
Yeah, it's pretty neat, isn't it? Look inside of some of those. They're neat. We got to find this height H right here, don't we?
Looks like a cabin.
Okay, let's talk about this, guys. Let's talk about this in terms of triangle 1, triangle 2, and then the big triangle. Okay, what do we have to solve for here, kids?
Height.
H. Okay. Guys, relative to triangle 1, what would H be? A long leg, short leg, or hypotenuse?
Short.
It would be a long leg, right? And on this one right here, we would have a hypotenuse of 25, just in this. Okay? So, another thing I could do, H could be part of triangle number 2, couldn't it? Where it would be the short leg in triangle 2. So, here's what we need to look at. Let's use triangle 1 to compare this. Let's compare H to 25 in triangle 1. Okay? Kids, I have a question. If we're looking at triangle 1 relative to H, is H a short leg, a long leg, or a hypotenuse here? Okay, so we're comparing in triangle 1. We're using triangle 1 for these dimensions. We're really comparing long leg to, in triangle 1, just look at this one right here. What would 25 be in triangle 1? The hypotenuse. So we're really comparing long leg to hypotenuse. So if we're saying H is to 25 in triangle 1, we got to set another ratio up where we know two values, but I don't care if you use triangle 1, triangle 2, or the big triangle. You've got to know a long leg and you've got to know a hypotenuse. Well, okay, so you're using the big triangle, right? Let's use the big triangle all the way out here. Quick question here, guys. Is 60 the long leg in the big triangle? What's the hypotenuse in the big triangle?
67.
So do we know two values from the big triangle? We're kind of comparing 1 to the big triangle. Okay, so what's the long leg in this again? You said 60, right? To, what's the hypotenuse in the big one?
65.
Okay. What I'm getting at here, kids, is this. We said, okay, we can say H is to 25 in triangle 1. That means we're comparing the long leg to the hypotenuse. But if I set a ratio up like that, I've got to find another comparison in a different triangle that compares the long leg to a what? Hypotenuse, the way I set this up. Here we go, kids. Isn't that just a proportion to cross multiply and divide now? So what times what first? 25 times 60. Somebody punch these up for me. 25 times 60, and then what do you divide by now, friend?
65.
65. So by cross multiplication and division, H must equal what? Do you get kind of a bad number?
0.0769.
How should we round? Does it tell us how to round it all?
23.1.
Says the approximate news. Should we go one place? Are you okay with that? I'm getting 23.1. Now guys, just take a look at the drawing. Somebody tell me why 23.1 seems like a reasonable number.
But it's shorter than the hypotenuse.
Yeah, it's shorter than 25, but this is a pretty steep pitch right here, right? So one would think this height's going to be shorter than 25, but fairly close to 25, isn't it? Are we fairly close to 25 feet from that diagram? Bet we are. Right? Bet we are. All right? Let's try another one.
That's it on that.
That's it on that page. Oh, it's such a pretty house. Did you find an A-frame yet for me, Michaela?
Yeah, it looks like a cabin.
Do you like them?
Not my favorite.
Okay, we kind of talked about this already. Geometric mean. The geometric mean of two positive numbers, A and B, is a positive number X that satisfies this. I think we're okay with this. So I'm just going to jump right down here. It says find the geometric mean of what and what, kids?
8 and 10.
Okay, so I would say 8 is to some number X as X is to some number what? 10. Okay. What you would end up doing, kids, is taking 8 times 10. What value is that?
80.
Now, kids, is 80 a perfect square? No. Okay. So what this would mean right here then is this. What this would mean, kids, is the following. You would take 8 times 10 to be 80. What's the other cross product in this when I set it up? What is X times X? So to get X alone, what do I have to do to both sides? Okay, so we would simply say, since 80 is not a perfect square, I would just leave it as square root of 80. Now, if they tell you to round that to the nearest 10th, that's going to be something that's pretty close to 9, isn't it? Because the square root of 81 would be 9.
So it's going to be 8.
So this is approximately 8.9. So sometimes you're not going to have nice numbers to take square roots of. Just leave it as a radical right here, okay? Square root of 80. All right, so this idea of geometric mean pops up. Here's the big idea today. There's two theorems I want you to understand. Are there a lot of words in these theorems?
Yes.
Would it be very bad if I said memorize them and you have to
Yes.
verbally tell them to me as a quiz? That would be very bad.
No, okay, because.
Yeah, once we got it down, but I want to know what it means. So here's my point. My point is, let's make some pictures to try and understand what the heck is going on here. Geometric mean, what's this say right here, kids? Altitude theorem. Okay, here's what I want to tell you. It says, I'll read this. It's going to sound really impressive, but it's not something you really need to know up here in words. We're going to put it in picture. In a right triangle, the altitude from the right angle to the what? Divides the hypotenuse into what?
2 segments.
The length of the altitude is the what? Of the lengths of the two segments of the hypotenuse. Draw your triangle kind of like this again. This is what they're meaning. And where do I want that right angle to be at again, kids? At the top. And when I draw my altitude in, my friends, here's what happens. There's my U through altitude. Okay.
Why doesn't the line go through the corner of what this is? It just really bothers me that it doesn't go through the corner.
Oh, through the very middle?
Yeah.
Because my triangle's not isosceles. That's why. I'm sorry. You're like me. I have OCD a lot and things like that. Little things like. How many of you are like at home? How many of you have a desk at home? Do any of you have a desk where everything does sit like perfectly or parallel? Like in my living room, I'll put the remote down so it's like in a certain spot, so it's angled a little bit.
Oh yeah, I do that.
Oh.
I just got to know.
What this is saying is this, kids. Here's what this is saying. If I have an altitude, do you guys agree with me? You agree my altitude right here is x? You agree with that right there?
Yep.
Okay, I'm going to call this the hypotenuse then down here, right? Okay. Okay. Think in terms of order of short leg, long leg, hypotenuse again. Okay? Look at triangle number 1 right here. Let's compare short leg to long leg. This would be A over what? Okay. This would mean A over X equals, okay, look at triangle number 2 over here, kids. Short leg would be what? Long leg would be, the ratio of short leg to long leg in number 1 is A to X. In number 1, it is X to what? Isn't this a definition of geometric mean right here? Where X is in the bottom here and X is in the top up here. Okay? We'll look at some examples of that here in a second. That's one of them. Right? Now, I'm going to try and draw the same triangle as best I can.
Well, that was pretty good.
It was, wasn't it? I'm impressed. Okay, drop your altitude in there again. This is your right angle. Maybe I want here. Well, I got to put the right angle in there because if I don't, life is very bad. Okay.
I make it so that it goes. Yeah, so it's like.
All right, here's the next one of this. Okay, all I want you to remember is this is called the. All I want you to remember is this. This is called the what theorem? Think altitude theorem. Think okay. Right there. Okay. Now the next one here, kids. This one's a little trickier, right? And in fact, this here is going to be a leg theorem. You don't know what the altitude is going to be, but it says in the right triangle, the altitude from the right angle to the hypotenuse divides it into two segments. So I have a segment here and here, right? Like A and B. Again, so label those A and B. Then here's the deal. It says the length of each leg of the right triangle is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Oh my gosh. It says the length of each what here, kids? I'm going to put an X out here. Okay? So what I'm gonna end up doing, kids, is this. I'm gonna call this triangle 1 and triangle 2. Talk to me about A and X right here, kids. A would be the short leg, wouldn't it? And X would be the hypotenuse. So if I compare short leg to hypotenuse, A to X, then let's see. We're comparing short leg to hypotenuse. Do you guys agree that the short leg in the big triangle is now X? That's going to equal X. But how about the hypotenuse in the,
A, B,
it's A and what?
B.
So down here would be A plus B, right? Okay, do I have a geometric, whoa, what happened there? Do I have a geometric mean with the X's again?
Yeah.
Okay. They're saying that this is the geometric mean of A and A plus B. So it's like part of the short segment and the whole segment. So let's look at some examples that deal with this. Okay? What's this called right here, kids? Okay, where is X at right here? Is that an altitude or leg? Where is X at in the big triangle for this? Is that an altitude or leg? Okay, let's try these here. See if we can't figure out what the heck is going on. On to that last page, please. Guys, these two examples, these are crucial. You need to know how to do this.
That's what you spell crucial?
I think so. I don't know. My English ain't so good.
It looks like, but it doesn't look like that.
Okay, guys, this X, it's unknown. Is this an altitude or a leg? So I can say that this is a geometric mean. Okay, so I can say 10 is to what? Kind of look at what I did. I went long leg, short leg as, in this triangle over here, X is to what? Guys, if you can just remember, if I'm looking for this altitude, think of it this way. What's 10 times 4 here, kids? 40, and then take the what? This would mean X squared is equal to 40. So X is going to equal what value? Square root of 40, whatever that is. Right? Here's what I'm going to kind of highlight for you. To find this length right here, it's the geometric mean of 10 and what other value? 4 then, right? So that geometric mean, it's going to be, you could say, okay, if I just take 10 times 4 and then do what? Okay, so let me just sketch one up here. Let me just sketch one right up here. Here's your triangle. Let me think of a good one.
Wait, can you, flip forward 10? It doesn't matter.
You could, because if the 10 was down here, you would have X up here, and the X would be down here, aren't they?
Yeah. Can you put 4 and 10 in that means? Yeah.
You could, yep.
Okay.
Okay. All right, what's 4 times 16 here, kids? 64. What's the square root of 64?
8.
So this distance right here is what? With me on that? Okay, that's what that altitude theorem means, okay? This is an example of the altitude theorem. Okay, now over here, what's unknown?
The leg,
Think big triangle. Is that y an altitude or is that y a leg?
leg.
Okay, so here's how this one sets up. Okay? I would say, well, let's just do it this way. Let's go y is to what here, kids? So y is to 3. Okay, now guys, if I put y up there, I want y to be the geometric mean, so where does y have to go for using geometric means to solve this? Okay, this is the one where y would compare to. So what we did is we went hypotenuse to leg in a small one, right? So we would have to do the hypotenuse of the big triangle, which is
8 plus 8.
8 plus 3 would be
11.
Okay?
33.
So here's how I would probably label this. To find y right here, you got to compare y with, you got to use the 3. Isn't the short leg next to y right here 3? You got to use this and really the whole other part of the hypotenuse. So I would say y is 2, 3 as 11. Isn't 11 a hypotenuse right here? To a short leg y. Okay, that's that theorem. What's 11 times 3, kids? So what's the square root of 33? Is that a nice number or ugly number? Just leave it as a square root of 33 there.
Wait, but why is y on top?
It doesn't need to be. I could have written it like this, Hunter, if I wanted to. I could have gone 3 is to y.
Would be y
as
squared.
Y is to 11, right? Okay.
Would the y be squared in that one?
If I cross multiplied, I would. I just kind of took a whole step out of it. Y squared would equal 33. So I square rooted reality to get y.
Oh,
And,
okay.
okay? So, Hunter, again, just a reminder. Geometric means mean that I've got one number that matches the, think of it this way. What's 2 over 6 would equal 6 over 18, right? Do you agree both simplify to 1/3? You agree both of these simplify to 3 now?
Yeah.
So as long as you've got one up top, one on the bottom, doesn't matter which side. Okay? All right, this last one, let's get through this. Don't quit early on me here. I want to finish this before we take off. Okay, using indirect measurement, kids. Guys, you know this already. I'm not even going to read this. Look at the example. What are we trying to find right here, kids?
Wait.
Okay, is this going to be an altitude inside here, or are we going to be using a leg theorem?
That's out.
Altitude right here. So 8.5 would compare to 5 and what? Okay, what's the geometric mean part then?
What, W over 8.5.
Okay, so we'll go W is 2. 8.5.
Which is equal to 5 over W.
Okay, we've got to be careful on this, kids. Altitude theorem, so that means the altitude has to be the geometric mean, right? Okay, so if I've got 8.5 down here, and I think it's a good idea, circle what we're dealing with. 8.5 is going to be the geometric mean right here. If 8.5 is down here like Olivia's already set up, 8.5 must go where?
That's out.
And the only other thing that's left is what then? Just check it out, guys. Let's see. W is a long leg, isn't it? In this top triangle, W is a long leg to a short leg, right? So this would be long leg to short leg. Let's see if it's got the same thing. 8.5 in the small triangle down here. Long leg to what again? Somebody cross multiply into 5 for me.
6.
You got a number there?
14.45.
14.45. I like it. I think that's right. Yeah. Yeah. 14.45. Okay. Now, guys, at some point, take a chance to read that. But you guys are good. You see the diagram right here. You're like, ooh, that's altitude. So altitude has to be the geometric mean. The geometric mean is going to show up twice in those proportions. Okay. Guys, going to start. I sent out a new online, so it won't be due till Tuesday. The extra credit one is due Monday. Do me one favor. Can you guys do me a favor?
Yep.
Enjoy.